Okay, CS161, lecture 19, TLS. That's not an impression of anybody, but again, I have to rack my brain to figure out who else has funny or distinguishable voices around here. Okay, so homework 6 should be out today in a couple of hours, and it should be due August 2nd, which is next Monday. I think we said we were going to release project design doc draft grades, and then we both forgot about it, so that's completely our bad. But they should be on Gradescope, I want to say today, and if not, just keep bugging us until it shows up. So sorry about that. And then the actual project is due next Tuesday. Okay, and then lab as always. Okay, last time was all about the kind of middle layer of protocols. So we started very low, talked about WPA, DHCP, ARP. And then yesterday was all about kind of the mid layer, layers 3 and 4. So at layer 3, we talked about a protocol called BGP, or Border Gateway Protocol. And this was the protocol for routing a packet across the internet to its destination. So maybe the destination for this packet isn't in the local network. So what we have to do is send it to the router, and the router has to find a different local network to send it to, so that it gets closer and closer to the destination. And what we saw was that the kind of high level idea of how this works is every autonomous system or a group of local networks controlled by like a company or a university will broadcast and tell all the other networks, these are the people I can reach through these routes. And then that broadcast kind of propagates outward until you hear somebody who is your neighbor tell you, oh, I can reach the destination by going from here to here to here to here to here. And then that lets us route the packet toward that autonomous system, who will then route it closer to the destination along the path. So that's BGP, but then we talked about there were attacks. We talked about some attacks on BGP. So if the autonomous system is malicious, they could broadcast a fake route, even if they're not on the route to the destination. They could pretend that they are on the route. So that could be a problem. And autonomous systems could also let people spoof packets, which we've seen. So those are the kind of attacks. And we said the defenses will be up to higher layers. So we'll deal with that today. And then we talked about TCP, which is the layer 4 transport protocol. So IP was good. It let us send packets anywhere in the world, but it didn't give us any reliability. So packets could get dropped. They could show up out of order. They could get corrupted. So TCP is a way for us to kind of patch up some of those. So to start a TCP connection, you run a 3-way handshake. It goes SYN, SYNAC, and then ACK. And the purpose here is for the client and server, which are the two people communicating, to agree on a set of initial sequence numbers. And then after the handshake, now that you have initial sequence numbers, you're going to send byte streams in either direction. So all of the bytes that go from the client to the server get a number. All of the bytes from the server to the client get a number. And both sides use the numbers to track if things are coming out of order or something has not been received and stuff like that. And we saw how you can use sequence numbers and acknowledgement numbers to say, well, this packet is the bytes starting at this number. And also, I'd like to acknowledge that I've received all of your bytes up until this number. So the numbers help us keep track of what's being sent. And then one extra feature that TCP gives us is ports. So maybe my computer runs Firefox and Zoom and whatever, and a bunch of different applications. So TCP, in addition to just sending between different IPs, it also sends between different ports within an IP address. So that way we can have connections between, maybe like I want to make a connection to 2 different machines and they're both sending me packets back. But because we're using TCP and there are ports, when my computer receives the packets from 2 different places, I can figure out that these packets are meant for this application and these packets are meant for this application. So those are ports. And then we talked about the attacks. So the main attacks are TCP hijacking and TCP spoofing, which are both kind of trying to inject your own data into the TCP connection or trying to start a TCP connection yourself. And we said these are easy if you're a man-in-the-middle attacker, because if you're a man-in-the-middle, you can just replace the packets in TCP. They're all in plain text. There's no cryptography, so you can just swap stuff out. if you're an on-path attacker, you can see all the sequence numbers, so you know all the values you need to successfully inject packets, but your packet needs to show up before the legitimate packet because the client or server generally only accepts the first packet. So you have to race to win if you're on path. And then if you're on path, it's even harder because not only do you have to race to win, but you also have to guess the sequence numbers. Because if the sequence number is all messed up, the victim is not going to accept your packet. Right? They're expecting a packet with this number, right, with like number 50 or something, but you give them a packet with number like 5,000. If it doesn't match, the client's not going to accept, or the victim's not going to accept your packet. So as an off-path attacker, because you can't see the packets and you don't know the initial sequence numbers because they were random, you would have to guess these sequence numbers before injecting. And that either takes a lot of tries or requires you to get lucky. So that was TCP. And then finally, we briefly talked about UDP. So maybe there are some scenarios where you don't actually want to send packets reliably. I actually don't care about reliability. I care more about speed. So maybe it's okay if a couple of packets get dropped once in a while, as long as the packets show up really fast and really often. So that's what UDP is. So UDP gives us the ports just like TCP, so you can talk to different applications, but there's no reliability, no ordering. It's basically just a plain old IP style packet with best effort. And with UDP, a lot of the attacks are easier because it's just a plain IP style packet. So there's no sequence numbers, there's no reliability or ordering or anything. So packets just show up whenever you send them, and it's best effort. Okay, so that was last time. And if you remember from basically the entire networking unit, a lot of the attacks we talked about so far have been like, well, this attack can happen, but it's kind of hard to defend. So let's use higher layer protocols. And we kept pushing everything off to the higher layer protocols. So today we can finally answer that question and tell you all about what is the higher layer protocol that magically defends all of these lower layer attacks. And that one is called TLS. So that's basically all of today. So here's the it's called the layering diagram that we've seen all unit. So we've talked about physical layer, which is sending the bits. We've talked about link layer, which is connecting up a local network. We've talked about network layer, which is connecting up a bunch of smaller local networks into a big global network. We talked about transport, which is making sure things arrive reliably and in order. And so today is this layer, which has a very funny number of 4.5, but this layer is going to be used to secure the transport layer and all the layers below it. So this is TLS, it's called transport layer security. And basically our goal today is going to be to secure our communications against attackers by using cryptography. And sometimes on the internet, you may have heard of something called SSL. And SSL was the old version of this protocol. So at some point they modified it so much that it, I guess, became a different protocol. So they had to rename it TLS. So that's fun. As we see here, again, the internet is built up of layers. So every layer depends on things below it and gives services to things above it. So TLS right here is built on top of a lower layer, TCP. So we're going to rely on TCP to give us the in-order message sending and the byte stream abstraction. So today, we don't have to worry about message length. So we don't have to break up messages into packets. We don't have to worry about messages showing up out of order. We don't have to worry about ports or any of that because we're on top of TCP. So all of that is done for us. We just have to use TCP to send our messages today, and we're done. None of that is important. And what this will provide to the higher layer is it's basically also a byte stream abstraction, but it's a secure one. So to the application layer, the highest one, which is like web, the abstraction for TLS and the transport layer, which is TCP, they look kind of similar, but the addition that TLS gives us is going to be all of those security properties. So confidentiality on our messages, integrity on our messages. Okay, I think that's basically the outline of what we want to see today. Yeah, so it's all about secure internet communication. So we do want to make sure things are secure, and we're going to use cryptography. So if you've thrown away all your crypto knowledge, I have to ask you to go and get it back for at least today, because we're going to use a lot of cryptography today to help us secure our communication. So these goals hopefully sound a little bit familiar from crypto. We want confidentiality. We don't want people to read our network messages. We want integrity because we don't want people to tamper with our messages. Again, these are basically copied from the crypto unit, but now we want them in a network setting. There's an additional attack that we want to prevent that we haven't seen too often, but it comes up. It's called a replay attack. So a replay attack is where if you're an attacker, or if I'm an attacker, maybe I see encrypted traffic. I have no idea what this traffic is because it's encrypted and it looks like a blob of random bytes to me. But on the network, maybe I can take this packet, even though I don't know what it means, and just copy it and then send another copy of this packet to the server. So the server actually receives this packet twice. Or maybe I do it again and the server receives this data 3 times or 4 times or 5 times. So even though I have not decrypted or violated confidentiality or integrity, I have given the server extra messages, like duplicate messages, and maybe the server will decrypt all of those and process them. So maybe this message happened to say, pay Mallory $100. And as an attacker, I copy this message in its encrypted form and then just send it over and over and over again. And the server will see the request to pay Mallory $100 10 different times. Maybe the server is now going to pay Mallory $1,000. So that's a replay attack, and we'll have to prevent that today. And then we saw this already, authenticity. So we do want to make sure we're talking to the right person. So the other person who's sending us messages, we want to make sure that they are who they claim they are and that they're not someone impersonating the server. So those are the 3 goals. Again, they're straight from crypto, except for this bonus replay attack that we'll talk about. Okay. Okay, so TLS, just like TCP or WP or some of these other protocols, it starts with a handshake. And so the handshake is going to let us establish a connection that's secure between the client and the server. And so we'll just walk you through the handshake, and then afterwards we'll talk about why did they design the handshake this way, what is going on here. But first, let's just see it in all of its steps. Okay, so the start is basically say hello. So I think these are actually the names in the spec, but it says, the client says client hello, and the server says server hello. So they're saying hellos to each other. So before any of this happens, first we should assume that there is already a TCP connection. So remember, TLS is built on top of TCP. So all of these back and forths that you see, we're going to assume that they're taken care of with TCP. So I don't have to worry if this client hello is super long and needs to be broken up into packets. TCP is going to do that for me. I also don't have to worry if the client hello messages show up out of order because TCP will do that for me. So all of that, all those jobs have been kind of abstracted away by TCP for us. So today we can just think of sending byte stream messages back and forth. Okay. So now the client hello message has a couple of things inside. The first thing is a random number, a 256-bit random number. We call it RB. I don't know why it's B. I think it's B for browser, but it's kind of annoying. So this is the client random, and it also tells the server a list of algorithms that it supports. So eventually they're going to have to use cryptographic algorithms to encrypt their messages, right? So they can say, I support AES CBC, or I support AES CTR, or I don't support AES GCM or something. So the client lets the server know my computer supports these different algorithms. Okay. And then the server replies with its hello. So the server also sends a random number. This one's RS for server. And the server hello chooses a set of algorithms. So the client said, let's use either this or this or this or this or this. And the server says, okay, well, you gave me these answer choices or these options. Let's use this algorithm and this algorithm and this algorithm. So they agree on a set of algorithms to use. Okay, so why did we exchange random nonces? So the reason here is already to prevent replay attacks. So the kind of intuition, and we'll see this a bit more later, is basically that if these are randomly chosen for every handshake, then 2 handshakes will always be different. So even if everything else in the handshake is the same, the client and the server are identical, all the other future steps are performed in the exact same way, because these 2 numbers are random, every handshake looks different. And that'll help us prevent replay attacks later. But for now, just note that this already immediately tells us that every handshake starts with a different set of numbers. Okay, so that's the first step. And now the second step is the certificate. So the server is going to send over its certificate. So again, we have to go back to crypto and reach back and get our certificate knowledge. And remember, the certificate just says, here's the server, here's their public key, and the public key is going to be signed by a trusted authority. So like a certificate authority. So all the certificate says is, this is the server's public key, and I, the certificate authority, endorse the fact that this is their public key. So now it's the client's job to validate the certificate, so verify the signature. Okay? And then if you do that, now you know the server's public key. So now the client at this point, after getting the certificate, is certain that this is the server's public key and nobody's tampered with it. Now they're not quite done here. Remember, we wanted authenticity and we wanted to make sure the server is not an impersonator. We're not quite there yet. And the reason why is because this server could still be anyone, right? What did they send over? They sent over a public key. And who can send public keys? Anybody can send public keys because they're public. So at this point, I do know the public key if you're the client, but the client does not know that they're talking to the server yet because certificates are public. So all the client knows for now is the server's public key. Okay, so that's the certificate. And now the next step is now we have to agree on a secret. So this step has two different purposes. The first step is now we're actually going to confirm that this is the real server and not somebody impersonating the server. And the second purpose is we're going to give a secret that the client and the server share, but nobody else knows. So there are two purposes to performing this next step. And the way we're going to ensure that the client is talking to the real server is we're going to ask the server to somehow prove to us, the client, that the server owns the private key. So the server has to somehow kind of perform a challenge or solve some sort of puzzle to tell us that the server owns the private key. And if we know that the server owns the private key, and we know that this is for sure the server's public key, then this must be the real server because nobody else would have the private key. So that's the reasoning we're going to use. Okay, so those are the purposes, and now I guess we can see what the actual steps are. So this step is kind of funny in that there are two different options you can choose. I think we talked about all of this. Yes. Okay. So there are two different approaches. We can use either RSA or Diffie-Hellman, and they'll both work in giving us a pre-master secret. So you choose RSA or you choose Diffie-Hellman, but you don't have to use both. So here's the RSA version. In the RSA version, the client randomly generates a secret. We call it the pre-master secret. And the client will encrypt the secret with the server's public key. And how does the client know the server's public key? It was in the certificate. And we know that that's the public key. So the client encrypts the secret with the public key, sends it to the server. Right? Now, if you remember from your crypto unit, if I encrypt something with the public key, the only person who can decrypt is the server. Any other attacker who sees this, whether you're a network attacker or you're an impersonator, you're impersonating the server, you have no idea how to decrypt this. The only person who can decrypt this pre-master secret is the legitimate server with the private key. So the server, assuming they're legitimate, they'll decrypt the secret because they have the private key. And now the client and the server share a secret. Nobody else knows the secret because the only people who know the secret are the client because they generated it, and the server because they're the only person who can decrypt this. Every other attacker has no idea what the secret is. So that's the RSA version. And again, we've proven that the server owns the private key because they're the only ones who can decrypt this. Nobody else could have decrypted this. So if this handshake completes successfully, as we'll see later, that gives us evidence that the server is the real server because they decrypted this. If they were an attacker, they would be stumped at this point because they don't know what the pre-master secret is. Okay, that's the first option. Here's an alternative. So this one uses Diffie-Hellman instead of RSA. And you've seen Diffie-Hellman before. We know that Diffie-Hellman is a way for us to generate a shared secret without an attacker knowing. So that's what they're going to do. So the server generates G to the A, the client generates G to the B, and then they exchange those, and then you get the shared secret, G to the A, B mod D. So that's the pre-master secret. It's the Diffie-Hellman shared secret. But Diffie-Hellman alone does not solve the problem of proving that the server owns the private key. Remember, the second purpose of this step is to make sure that the server owns its private key. And Diffie-Hellman by itself does not do that because you're just exchanging random values. So in addition to regular Diffie-Hellman, there's one extra bonus step here, which is that the server is going to sign its part of Diffie-Hellman. So it still sends G to the A, but it also sends a signature on G to the A, and the client's going to verify the signature. If the signature is correct, that means we're talking to the real server, because the only person who could have signed this correctly is the server with the private key. Any other attacker at this point trying to impersonate the server without the private key would not be able to perform the signature, and they would fail here. So regardless of which option you choose, you fulfill both purposes. You show that the server has the private key, that you're talking to the real server, and you settle on a secret that only the client and the server know and nobody else knows. And remember, the Diffie-Hellman guarantee is even if you see G to the A and G to the B, there's no way for you to learn G to the AB. So that's the kind of other option for premaster secrets. Someone asked if someone can replay attack this. So do you mean just replay attacking the G to the A mod P with the signature? Yeah, I guess you're right. That's a good question. We'll see how that's stopped really soon because the way it's stopped is going to be, it's going to involve the hellos. But that's a good question, and we'll see the answer hopefully really soon. Okay, but either way, at this point, you have a pre-master secret. So whether you chose RSA or you chose Diffie-Hellman, at this point, the client and the server share a pre-master secret that nobody else knows. Because we have a secret, we're ready to derive symmetric keys. So let's do that. So we're going to derive symmetric keys from 3 different values. We're going to use the random values from earlier plus the pre-master secret. This might feel a little bit familiar to you if you remember the WPA handshake. So the WPA handshake, what do? We took the nonces, and then we took a pre-something key, a pre-shared key or something, right? And then we use those to derive symmetric keys. So actually the pattern here is exactly the same. We take the random nonces, combine them with our preliminary key to get our final symmetric keys. So it's exactly the same. And usually the way to do this is you take a PRNG and you seed it with these 3 values, but it's not too important how that works. So the thing to note here is that if any of these change, you get different keys. So if it's a different handshake and RB and RS are different, you get different keys. If the client chooses a different pre-master secret, then you get different keys. So this is kind of weird and it takes a while to wrap your head around, but there are actually 4 symmetric keys that come out of this derivation. And this is basically related to the thing where we said you can't reuse keys. So not only are we going to not reuse keys, but we're actually going to be super paranoid and create different keys for each direction. So for the client to server messages, we'll use an encryption key. For server to client messages, so in the other direction, we'll use a different symmetric key. For macking client to server messages, we'll use a different key. And then for macking client to server messages, we'll use yet another key. So there are 4 keys in total. And note that both sides know all 4 keys. So even though we're using like one set of keys in one direction and another set of keys in a different direction, everybody knows all 4 keys, so they can always encrypt and decrypt stuff. The reason why we use 4 is just to avoid key reuse and also to be a bit paranoid. Okay, so at this point, both sides have computed keys, and note that they're doing this offline. So it's not like they're sending these keys to each other. They both have the secret. They agreed on it from before. They both have the random values from before. So they're going to compute all of this offline. So nobody else can see that these keys have been derived. Okay. So we're almost done. We're almost there. The 5th step is to exchange max. And at this point, we're going to prevent a lot of other attacks. So in the handshake so far, we've sent a lot of stuff back and forth, right? So we've sent a Diffie-Hellman exchange, possibly some RSA stuff. We sent hellos, we sent a certificate. A lot of stuff went over this channel, and some of it was in plain text. So like, we have no idea if someone tampered with the random values here, or maybe they tampered with this encryption or the signature or G to the B mod P or something. It's very possible that any of this stuff could have been tampered with. So we have to find a way to detect that. And that's what step 5 is for. So now we're going to use cryptographic max because we have symmetric keys. And the cryptographic max will help us detect any tampering on anything from before. So we'll just take everything that was sent from earlier, put a MAC on it, and then exchange the MACs. And at this point, if anything had been tampered with, the client and the server will get different MACs. So the MACs will no longer check out. Right? So like if a client sent something, but the attacker tampered with it, and the server received something different, then their 2 perspectives will be different. And if they have different perspectives of what's happened so far, then their MACs will be different and everything will fail at this point. So if you try to replay, I guess depending on the circumstances, if you try to replay the G to the A mod P step here, if you're doing so as a man in the middle, chances are you'll get caught with the max because the server will think it sent this. The server will think it sent its own G to the A mod P, but the client will receive a different G to the A mod P because the attacker tampered with it. So the MACs will no longer check out. So if you're a man-in-the-middle attacker, that's where you'll get caught. If you're someone impersonating the server and sending this copy, that's a little bit harder to reason about, but I think the whole handshake would fail because of the random nonsense at the beginning. So if you're copying this from a previous connection and you're trying to impersonate the server, I don't think it would quite work because you wouldn't be able to come up with the symmetric keys later. But feel free to ask about that offline because reasoning about the handshake sometimes takes a bit of thinking. Maybe Nicholas can answer in chat, but that's definitely a good question. And reasoning about MACs or reasoning about the TLS handshake is something valuable. But anyway, at this point, you compute MACs. Remember, these are not MAC addresses, they're cryptographic MACs, or MICs if you prefer to rename them. Okay. And now we're finally done. So now we're finally ready to send any message that we want. And every message that we send from here on out will always be encrypted and MAC'd. So every message has encryption, so confidentiality, and it has MACs, so it has integrity. One thing that you might notice here is if you squint carefully, this is actually not encrypt and MAC, which we said was the better one. It's actually MAC'd and encrypt. And someone brought this up, I think a couple semesters ago. And they said, they asked on Piazza or something, they were like, why does TLS use MAC'd and encrypt? And we asked around Stack when we turned out, nobody actually knew the answer. So it was off to Stack Overflow or something to find out. And we dug around and we found out that the answer is, it's kind of stupid, but the answer is just legacy. So back in the day when TLS was first developed, somebody had the option between these two and had no idea which was better. So they just chose MAC'd and encrypt. And they were like, oh, well, let's just go with that one. And I guess nobody bothered to fix it because they thought this was good enough. And so it's just stuck around for quite a long time. Although at some point, I think it was TLS 1.0, when we saw this in the crypto lecture, because they used MAC'd and encrypt, it actually got attacked by the Lucky 13 attack. And that was, I think, when TLS figured out that something was wrong. But for a very long time, TLS did use MAC'd and encrypt just because nobody knew better. So again, that's kind of the level of security in network security. Sometimes people just do things because that's the way it's been done. And until they get attacked, they don't fix their shit. So good job. So that's the whole TLS handshake. Now you've seen the whole thing. And now we can kind of slow down and think about, wait, what were any of those steps we just saw? So why did we do all this random stuff? Did it actually help us solve all those problems that we wanted to solve? So one problem that we wanted to solve is we wanted to talk to the legitimate server. We do not want this person to be an attacker. So how did we guarantee this? We already saw this, right? The server sends its certificate. That guarantees to the client that the server's public key is correct. So the client at this point has a correct guaranteed version of the server's public key. And the server has proved that it owns the matching private key. So either using RSA or Diffie-Hellman, the server finds a way to prove that it owns the private key. And by doing so, the server has now proved that they are the real server because they're the only person with the private key. So either they decrypt the pre-master secret, which only the server can do, or they sign their half of the Diffie-Hellman exchange, which only the server can do. And if you are impersonating the server, we're going to assume that the attacker has not stolen the server's private key. So that's something we have to assume. If the attacker has stolen all the server secrets, then the attacker could possibly impersonate the server. So we do have to worry about that. Okay, the second thing we wanted to guarantee is confidentiality. So we wanted to ensure that all the messages are secure and that attackers can't read them. So how do we ensure this? Well, if we think about how the attacker would try to get these keys to decrypt, remember the keys come from the pre-master secret. So the attacker doesn't know the pre-master secret because either in the RSA option, the secret is encrypted with a key that they can't, it's encrypted with the public key and they don't have the private key to decrypt. Or in the Diffie-Hellman version, the Diffie-Hellman property says, given G to the A and G to the B, I can't learn the secret. So either way, the attacker cannot learn the pre-master secret. If the attacker doesn't know the pre-master secret and the keys come from the pre-master secret, then the attacker doesn't know the keys either. So if you think about that, if I don't have the input to generate the keys, then I can't generate the keys. So the attacker doesn't know the input and can't generate symmetric keys. So this means that we have confidentiality and integrity because the attacker has a hard time learning what the pre-master secret is. So our messages are also secure. That's good. And the final thing we have to worry about is replay attacks. So let's think about this. how do we make sure that someone doesn't take messages from a previous TLS connection and try to shove them in here? So maybe the attacker saved a bunch of values from a previous connection and tries to inject them into this connection. That could be a problem, right? Because I don't want the attacker to save a message like pay Mallory 100 from a previous connection and then just start flooding it over and over in this one. So the way we solved that was every handshake uses a different RB and RS. So by definition, every handshake starts with a random set of values. And these random values are used to derive the symmetric key. So every single time you run a handshake, the symmetric keys are different. So I can't take a message from a previous connection and shove it in here because they'll have been encrypted with different keys, so they won't decrypt correctly. So that's how you would stop replay attacks within different connections. But what if someone tries to replay attack within the same connection? So they see a message in the same connection and then immediately send copies of that replay or send copies of the packet to do a replay attack. So how do we stop this version? This one requires one extra kind of feature. So in addition to just sending messages, we are going to add something called a record number. And a record number basically numbers every TLS message with a unique number. So this way, if I replay a message as an attacker, the record number will show up repeatedly, and that's not going to be accepted. So the server is expecting a different number for every message, right? So if it sees pay Mallory $10, record number 10, pay Mallory $10, record number 10, pay Mallory $10, record number 10, over and over, it will see, wait a minute, these are not unique record numbers. So somebody is probably replaying all these to me. So I'm going to ignore all the duplicates. If the client legitimately wanted to send this message 10 times, it would really look like pay Mallory $10, record number 10, pay Mallory $10, record number 11, pay Mallory $10, record number 12, 13, 14. So if the client legitimately resent this over and over, they would use different record numbers. And if the record numbers are the same, that's an indicator to the server that a replay attack is going on. So this is clever, but it's easy to confuse these with TCP sequence numbers because you're numbering messages. So wait, why are these different from TCP sequence numbers? So these are for security. They are encrypted inside the message, so attackers cannot read these record numbers. They're only used for security between the client and the server. But TCP sequence numbers are not encrypted because they're used for rearranging packets. And they're used in the lower layer. So remember, all of this stuff, the messages, the certificate, it's all sent over TCP. So the TCP layer below this has to still use sequence numbers to rearrange the encrypted packets before anyone can run decryption. So those are unencrypted numbers in the TCP header, and then the record numbers are inside the TLS header, and those are encrypted. So it's very easy to confuse these two, but they're used for different purposes. Okay. So those are the ways to defend against replay attacks. Let's quickly talk about forward secrecy, which is something we've talked about a lot. Remember, the property here is, let's say an attacker records a connection now. So they get all the encrypted stuff that's been sent over the network. And sometime in the future, they compromise secret values. So maybe they haven't stolen the server's private keys yet, but later they will. So forward secrecy is the property that if this happens, that they record a connection now and compromise values later, they cannot actually decrypt the recorded connection. So even though they recorded these encrypted values, in the future, even if they compromise the server, they have no way of figuring out what the connection said. So forward secrecy is not guaranteed in RSA. And the reason why is because if you record the entire connection, you get RB, you get RS, and you get the encrypted premaster secret. If sometime in the future you compromise the server's private key as an attacker, then the attacker can decrypt the premaster secret because it was recorded. And if you have the premaster secret decrypted, you have the random values, you can derive the keys. And if you can derive the keys, you can decrypt everything. So RSA TLS does not have forward secrecy. But Diffie-Hellman TLS does have forward secrecy. And the reason is because Diffie-Hellman is ephemeral and it gives us forward secrecy. So as soon as the TLS session is over, we actually delete the premaster secret, the G to the AB, that's deleted. Right? And if we delete the premaster secret, then maybe the attacker has recorded the entire connection, but even if they learn the keys, they have no way of learning the symmetric keys. So they can steal the server's private key, that's all fine, but they still cannot decrypt old recorded connections. And the reason why is because if you remember the Diffie-Hellman exchange, there was G to the A and G to the B, but we remember from Diffie-Hellman that that's not enough to generate G to the AB. So that recording does not help the attacker learn the secret keys, even if they have the surface private key. So Diffie-Hellman does have forward secrecy. And I guess one thing to note here is not quite related to forward secrecy, I don't think, but you remember from Diffie-Hellman also that there was a man-in-the-middle attack. So there was an attack where, as a man in the middle, you performed a Diffie-Hellman exchange with both sides so that they agreed on different keys. But that actually cannot work here because the Diffie-Hellman component is signed. So the additional signature will stop that man-in-the-middle attack. And feel free to think about that on your own or ask about it later if you want to see more about it. Okay, but I think it's enough just to know that because the man in the middle does not have the surface private key, they cannot sign their half of the Diffie-Hellman, so they can't do the man in the middle attack from before. Okay, that's forward secrecy. And because we noticed that, wait a minute, there were two RSA, there's two options for TLS. There's RSA and Diffie-Hellman. And it turns out there's actually a property where one of them is strictly better than the other, right? Because of forward secrecy, Diffie-Hellman is actually like the better version. So if you're given the choice, you should basically always use Diffie-Hellman. So eventually the TLS designers realized this too, and they said, you know what? If one of these is absolutely the better version, why are we even letting people use the worst version? So the TLS people realized this, and they released a version called 1.3. I believe this is still the latest version. It was released in 2018. And in TLS 1.3, they threw out the RSA version. So if you're using TLS today and using this latest version, you cannot use RSA. They threw it out. They said RSA does not have forward secrecy. Stop using it. Only use the Diffie-Hellman version. And that gives us forward secrecy. They also fixed a couple other things. There's a performance optimization. I don't think this is too important, but basically they realized that if RSA is no longer an option, the only option left is Diffie-Hellman that most people will use. So let's just save some time, and instead of exchanging G to the A, G to the B within a separate step later, let's just send them in the hellos, because we figure that almost everyone's going to default to using the Diffie-Hellman exchange. So that kind of saves us a couple of round trip messages, right? So instead of going back and forth and back and forth and back and forth and send G to the A and G to the B, the server and client can just knock those out inside of the hello messages to save them a bit of time. So that saves us a bit of time because RSA is no longer an option, and we know that everyone's using Diffie-Hellman. And finally, we saw that MAC-then encrypting was not secure because of the Lucky 13 attack. So the TLS people also saw this, and they said, why are we still using MAC-then encrypt? That's pretty horrible. So they have actually switched to using an authenticated encryption mode, and we saw these earlier as well. These are the block cipher modes that give us both confidentiality and integrity at the same time. And the TLS designers were very careful to implement this correctly so that I get both at the same time. So modern TLS is a little bit different from what you see in these slides. It could honestly just be because these slides are super old and we just updated them this semester. I don't know. But the very modern state-of-the-art TLS, it only uses Diffie-Hellman and it only supports authenticated encryption. So no more MAC-then encrypt problems. Okay. I think that brings us to the end of the actual TLS protocol. So does anyone want to ask questions before we maybe take a break and then start talking about what does TLS actually look like in the real world and how can I try this at home? So before we do that, any questions? All good? Okay, yeah, for TLS, I think the main thing you should know for, I guess, exams and for going forward is definitely just go through the handshake. It's kind of long, but it has a lot of steps, but they're all important. And make sure that you understand every step of the handshake and that you can explain why is the step of the handshake needed and what could be the consequences if I take it out. Someone asked about forward secrecy of Diffie-Hellman. Yeah, sure, we can slow down and refresh that one. So the forward secrecy of Diffie-Hellman comes from the fact that, remember, forward secrecy says if I record a connection now and I steal secret values later, I still cannot decrypt the recorded connection. So let's say an attacker records all of this stuff. They record the hellos, they record the certificates, they record the Diffie-Hellman stuff, and they record all the messages. So they have that now. And then time passes, and in the future, they learn the server's private key because that's the thing that the server is always storing. In Diffie-Hellman TLS, the server's private key does not help them learn the symmetric keys from this handshake. So this handshake plus the server's private key is not enough to learn the symmetric keys. Because if you look at this recording, what you need to learn the symmetric key is the pre-master secret, which is G to the AB. But using these two values from Diffie-Hellman, we saw it was impossible to learn G to the AB. So stealing the server's private key does not help us here. So that's how forward secrecy works. And the main reason why it works is because Diffie-Hellman is ephemeral. So as soon as the server and the client are done talking, they're going to abandon their G to the AB. So the G to the AB value is never saved anywhere. So even if the server or the client is compromised and the attacker steals all their secrets, G to the AB will not be one of the secrets because it's been discarded already. So that's why Diffie-Hellman gives us forward secrecy. It's because the recorded values do not tell us what the symmetric keys are. So just looking at these don't tell us what the symmetric key is. And the second reason is because the actual symmetric key derivation values, like the pre-master secret G to the AB, are thrown away as soon as every connection is over. So those are the main reasons why Diffie-Hellman has forward secrecy. Okay, sounds good. Any other questions? Okay, I think that's enough awkward silence for the folks on recording. So let's pause the recording. Let's come back at 4:26 to talk about what TLS looks like in the real world. Okay, welcome back from a pretty uneventful break, but that's okay. Everyone got some rest. So the rest of this lecture is mostly about how TLS looks in the real world. So as you'd imagine, almost everyone on the internet should or does use TLS these days. So now we're going to take a look at what are the consequences, I guess, of implementing this protocol on a global scale where like almost every person on Earth who uses the internet is using TLS in some form. So that is a very big logistical challenge, and we'll basically talk about it today. So I think most of this lecture from now on is going to get a bit more conceptual. So we've gone through the nitty-gritty crypto details. And from now on, it's just kind of a conceptual look at, well, what does this look like in the real world? So before we do that, I guess we should talk quickly about a couple of like properties that it gives us in practice. So first, how efficient is TLS? Is it fast? Is it slow? Well, let's kind of go through the pieces and analyze it. So TLS uses public key cryptography in some form. Either it uses Diffie-Hellman or it uses RSA. Today, it's always Diffie-Hellman. That gives some minor costs because public key cryptography is slow, but you're only using it once per connection, right? You only use it for a single Diffie-Hellman or a single RSA encryption. So it's not too bad, it's minor. Yeah, like I said that. Symmetric key cryptography, now we have to encrypt every single message that we send, but that's effectively free today because we've talked about this before. Modern hardware is extremely fast with symmetric cryptography. It's all XORs and bit shifting, which are super fast. And modern hardware is so fast that it even specifically wires things to support very fast encryption. So yeah, you do have to encrypt every message before you send it when you're using TLS, but there's basically no cost to that. So really, why would you not encrypt your messages? If there's no performance impact, I don't think in modern days you'll ever feel slower using TLS than when you don't use TLS. There's one slight thing that could affect speed, and this is before the first message. So before you send a single message in TLS, you have to perform that entire 10-step handshake, which could take some time. So after the first message, it gets really fast, but if you really care about speed in the very first message, or if you're just sending one message, it could take something like 11 round-trip messages before you can even fire off a single message. So that could affect your speed a little bit, but in general, TLS today is basically free, so there's no excuse not to use it. Okay, now we can talk about kind of the glorious property that TLS gives us, which is end-to-end security. Why is this so great? Because end-to-end security means there is no need to trust anybody in between the two endpoints. So literally every single person between the client and the server can be an attacker, and TLS is still secure. That's kind of like mind-blowing to me that this is even possible, but it is because of the way we designed TLS. So if you remember from all the previous internet lectures, right, the client wants to send a message, so it'll have to take the message, maybe use ARP, which has attackers, send it to a router, which the router could be an attacker, The router sends it to different autonomous systems. The autonomous systems could be attackers. The final autonomous system sends it to the final destination. The computer at the final destination could be an attacker, right? Like the operating system. Basically anything along the path of TLS can be evil, and all of it can be evil, and it doesn't matter. TLS is still secure all the way because everything is encrypted in MAC, and there's no way to perform replay attacks or impersonate the server or anything. This entire path is secure. So that's kind of a crazy thing to think about, but it's so powerful and so great because all those lower layer attacks that we talked about, DHCP, WPA, I don't know, TCP, they all have these different attacks. And the reason why we could be so casual with them and just say, you know what, forget it, let's just use higher layers, is because this higher layer is just that good. It gives us end-to-end security. So, wow, that's kind of mind-blowing. There is kind of a slight problem here, which is that it is end-to-end. So that doesn't mean if one of your endpoints is malicious, you're kind of screwed. So this doesn't help you if you're talking to like a malicious server, right? So yeah, your connection to the malicious server is secure. Anybody between you and the malicious server cannot tamper with your connection, but you're still talking to an attacker, so that's still not very secure. So you can have a TLS connection to an attacker, and that's no good. But TLS does protect you against any network attacker in between the two lanes. So that's great. So we talked about some of these, right? Maybe an attacker wants to read a Wi-Fi session, but they can't because TLS encrypts them. A man in the middle could try to do TCP packet injection. They can't do that either because the packets have MACs on them, so their injection will not succeed. Even if they're man in the middle and they try to inject packets, which we said was easy yesterday, now it becomes hard because they're MACs. So this is great. This solves all of our problems with a single protocol. So life is, it's good sometimes. Okay, so this is how all those attacks from yesterday got defended against. Okay, but even though this is so great, TLS is not perfect. So it's not like it solves all of our problems. Here are a couple that it doesn't solve. So it doesn't give us anonymity. And we'll talk about anonymity a lot more in, I think, the last lecture, which is tour. But anonymity is the property where we hide identities from attackers. So we don't want the attacker to know that I today am talking with Google, or if I'm talking with Yahoo or Bing or one of those other search engines. DuckDuckGo is nice, so maybe that. Right, so TLS does not actually hide who is communicating with who. And the reason why, well, there are a couple of reasons why TLS leaks this information. First of all, the TLS handshake has a certificate. The certificate is public and is sent over plain text in the handshake. So an attacker could just read the certificate and find out, oh, this person is talking with this server. That's kind of easy. The client sometimes also indicates its name, sorry, the client indicates the name of the server sometimes. So in the client hello, sometimes it'll say, hello, I would like to connect to Google, or hello, I would like to connect to Berkeley or something, right? So that comes up sometimes, and that would also allow the attacker to read who's communicating with who. And kind of the biggest reason is any packet has IP addresses in the IP header. So even though the TLS message is encrypted in the higher layer, remember how you wrap all the headers around as you move down the stack? So as you move to lower layers, you have to wrap an IP header, and the IP header cannot be encrypted because all those autonomous systems and stuff, they had to figure out where this packet goes. So the IP header is not encrypted. The TCP header is also not encrypted because you have to rearrange messages. So all of that is in plain text. An attacker can look at any packet and see its IP addresses and ports and figure out who is who. So that's a problem. So TLS is great, but it doesn't hide who you're talking to. So if you're trying to figure out a way to hide who you're talking to, TLS will not solve that for you. One thing TLS does not provide is availability. We'll see this again, I think, next week when we talk about denial of service. But availability is keeping the connection open. So I would like my messages to successfully be delivered, even if an attacker is trying to stop me. But the problem is TLS does not have this. An attacker can stop TLS connections. So for example, the man in the middle can look at all these encrypted packets and say, you know what? No, it's like gonna block it, right? Just bat it away. So an attacker can stop a TLS connection by just dropping every packet. They can't read the packets. They can't tamper with the packets, but they can drop them. And if they keep dropping them, then your connection will never go through. So the attacker can stop you. And this one's kind of weird, but the attacker can actually do reset injection to stop the underlying TCP connection. So let's think about this. Remember, TLS is built on top of TCP. So all of those messages in TLS, they rely on TCP to give us the reliability. That also means that if someone stops the TCP connection below, the TLS connection will also break because it's relying on TCP. So those attacks from TCP are still possible. If I do a reset injection on TCP, that stops the TCP connection. It's true that the TCP connection is sending secure stuff, but I can still stop the TCP connection with a reset injection. And the sequence numbers are not encrypted or anything, so I can do that. So if an attacker does reset injection and the TCP connection is aborted, then the TLS connection will also break. So there are several different ways to stop a TLS connection from happening, even if you can't read or tamper with the messages. So that's another problem. Okay, and we'll see this also, I think, when we talk about censorship. So if you want to censor somebody, you can censor a TLS connection. You can't read what the TLS connection says, but you can figure out who they're talking to. And then if they're talking to someone you don't want them to talk to, you can censor them. So that's a way to do censorship. Okay. Let's talk quickly about how TLS works for applications. So remember, we got all the way up to layer 4.5. Now let's make the final leap to the highest layer so that we're all finished. So what's the only layer above TLS? It's the application layer. What kind of applications are there? There's a lot. The most common one is HTTP, which we've already seen. HTTP is an application layer protocol, and it runs over TLS, or it can run over TLS. So this is why in the web lecture we talked about HTTP versus HTTPS. We're like, wait, why does one of them have security and one of them doesn't? It's because HTTPS runs with TLS, so it encrypts all of its messages. HTTP runs over plain TCP and there's no TLS. So that's the difference between those two. And that's an example of an application that either uses TLS or just TCP. There are other secure application layer protocols, right? So you don't have to always use HTTP for web requests. You can basically do anything that uses a byte stream abstraction. So for example, if I'm sending email, I can use TLS to send emails. And the email protocol isn't quite HTTP because we're not delivering web pages, but you can still use TLS to run emails. So the application layer can run different applications over the same TLS protocol. So there's email, there's SSH, I think also can use TLS, although I'm not sure if it does, but stuff like that. And TLS, however, does not defend against application layer vulnerabilities. So this is kind of like the end-to-end property from before. If you're talking to an attacker, TLS is not going to stop you. So all those web attacks from before, SQL injection, XSS, CSRF, those are all still exploitable over TLS. And the reason why is because they're happening at the application layer. So if you talk to a server that's vulnerable to any of this stuff, TLS is not going to help you. It's true that nobody can tamper with your message, but if you talk to a web server and the web server decides to give you malicious JavaScript, you're stuck anyway, because you're talking to a malicious server. So you have end-to-end security, but the other end is malicious, so it's not good. Okay, so that actually finishes, I think, the entire stack, which is kind of cool. And I think the rest of these lecture slides, are almost all blue, so it's almost all for fun, but some of them are kind of interesting, so let's just talk through a few of them. This one's kind of interesting. It's called SSL stripping. And this one happens because when you type addresses in your browser, does anyone ever type http:// or // berkeley.edu? Or do you ever type https://cs161.org? I don't think anyone does this, right? And the browser is smart enough to know this, because if you just type berkeley.edu or cs161.org, doesn't the browser just add it for you, right? And sometimes you look in the browser and they added it for you. So I think a lot of people hopefully have seen this, right? The problem is a lot of browsers just default to HTTP. So they don't use the TLS version, they use the non-TLS version, because that's what most websites supported back in the day, before TLS was everywhere. So if you just type cs161.org, the browser would take you to the unencrypted version of that website that doesn't use TLS. And that's a problem, because some websites do not want you to access them without TLS. Like if you're talking to a bank, you should not talk to a bank without TLS. You don't want network attackers to see your bank information, so you would like the bank to redirect you to a TLS connection. So what the website will do is it'll say, oh, you want to visit the httpbank.com website? I will redirect you to the HTTPS version. So you rarely see this in your browser because it happens instantly. But often what happens is you make a request to the HTTP version. The HTTP version of the website gives you a response and says, don't talk to me, talk to the HTTPS version. And then your browser makes a second request to the HTTPS version, and that's how you get the HTTPS version of the website. Right? But this requires the client to first receive the unprotected version. So even though eventually you hit the secure bank website, you first had to talk to the bank with an unprotected HTTP response or request. And that version does not have TLS. So what can happen if you talk to an attacker or talk to a server without TLS just once? All future requests are good, but what if your very first one is not encrypted? That's enough for an attacker to come get you. So what happens is the attacker finds a way to force the victim to use unencrypted HTTP. So here's how this works. The user makes an HTTP request, right? It wants to talk to bank.com, it defaults to HTTP. The attacker stops it right here and makes its own HTTP request to the server. This means the server never receives the redirect. So because the attacker stopped it right here, right? So this request was supposed to go all the way to the server. The server was supposed to come back and say, hey, use HTTPS. But it never got there. The attacker stopped it. So this HTTP request went to the attacker. The attacker stopped it right here and said, I will feed you information from now on. And from now on, every request always goes from the user to the attacker insecurely, from the attacker to the server securely, from the server to the attacker securely, and then from the attacker to the user insecurely. So this has made the attacker a full man in the middle because they stopped the initial redirect. So that could be a problem. And they can stop the initial redirect because the first message came through HTTP, and that's not secure. So this is a stripping attack, and basically what it did was it forced the user to downgrade to a less secure version. There is a defense these days, and basically the defense is called HTTP strict transport security. This is a header inside the HTTP packet that tells browsers you should only ever talk to me with HTTPS. That should be S, sorry. So that's a modern defense. Okay, but that's all blue, so it's just kind of a fun attack. Let's talk a bit about how users see TLS. So if you're a user, maybe you've never seen TLS before until this lecture, which is totally fine. I didn't know about TLS until this lecture when I took this class, I think 2 years ago, 3 years ago, scary. But what does a user see when they see TLS? Well, let's see. So if your browser is using TLS, you see that little lock icon, and we'll show it to you in just a moment. If you're not using TLS, you don't see the lock icon. So the lock icon is supposed to communicate to the user that you are doing something securely, because the user sees the lock and thinks, oh, locks are secure. So the lock tells the user we have a encrypted communication and we're talking to the legitimate server. Now, the user might not know this, but that is what the lock icon is supposed to communicate, right? And also, if the lock icon is present, any external images usually come over TLS as well. So here's an example from an older browser, right? This is the original design. This website is using HTTP. So if you look at it, there's no lock icon. Right? This website is using HTTP, so you see the green lock. And for a user, this is how a user who doesn't know about TLS is supposed to know, I'm talking securely here, but I'm not talking securely here. Do most users notice this? Not really, but if you care about security and you're concerned, this is what you look for. And this is how the browser communicates to you whether you're being secure or not. This is good, but it's not perfect, right? Because let's say you look at this top one right here. So you look at this one without any lock icon. To you, maybe this does not look insecure. It is insecure. Now we know it's insecure because it's HTTP. The network attacker can do anything. So this is insecure, but to a user, they don't see that, right? They just don't see the lock. But maybe they're not always thinking about the lock. So they don't see this and think, hold on, there's a missing lock here, right? Like who does that? Who goes to a website and immediately notices that there's a tiny missing lock button here? So this is not the best design because we are not explicitly telling users when things are insecure. We're only telling them when it's secure, and when it's not secure, we're just kind of defaulting to a plain looking interface. So we can do better. So let's do a bit better, I guess. Sorry, I'll come back to this in a second, but let's talk about the modern design. So the modern design, not only does it tell you if connections are secure, it actually tells you when connections are not secure. So let's add an icon to tell people when things are not secure. So let's see what this looks like. This adds a signal on unencrypted websites so that if you're going on an unencrypted website, you don't just see the default from before. You actually see a real message or real icon that tells you, I am not being secure right now. This also has a funny side effect of encouraging websites to stop using HTTP, because if you are trying to sell something to someone, or you're trying to, create a website that you want people to visit, how good is it, or how bad is it if your website always shows people a gigantic flashing not secure sign? Do you really want people to associate your website with being not secure? Probably not. So this is kind of an encouragement for websites to get their shit together and use HTTPS. So let's take a look at this. This is something I grabbed from today. So this is a modern browser. This is example.com. It's not secure. And how do we know that? Because Firefox now shows you this no lock sign. This explicitly tells the user you are currently not on a secure website. If you're secure, you see this lock icon like before. So now, not only do we show people when things are secure, we show them when things are not secure. And if you're running a website and you want people to come to your website, you probably do not want this icon next to your URL, because you're giving people the impression that things are not secure. Okay. That's the modern design. One thing to talk about, I guess, is the users are not totally aware of all of the ramifications of a lock icon. What do the users think? The users just see a lock and think, oh, it's secure, right? Do they know where the lock icon is showing up? Maybe not. Do they know if the lock icon is real or a fake one? Not really, right? How do you tell? So there are a couple of attacks that attacker can do here, and these are kind of like the UI attacks from a couple of weeks ago. So an example of a user interface attack is, if you're on an attacker's website, let's just put a lock icon somewhere, right? It doesn't have to be in the browser, it could just be anywhere. And that might fool the user into thinking, I must be using a secure website because there's a lock icon. But is this website really secure? No. Right? Or the user might be communicating with an attacker's website over TLS. We saw this already. TLS is end-to-end secure, but it doesn't help us if we're talking to an attacker. So this is a problem because you actually see the real, legit lock icon from Firefox or Chrome. The browser shows you the real lock icon, so you think you're good because you see the lock as a user. But are you really secure? No, because you're talking to an attacker. So the lock icon is not perfect because users may not be actively thinking about TLS. So they could be fooled by a fake lock icon, or if they're talking to an attacker, they see the lock icon and they think they're okay, but they're not. So these are all problems. Okay. So this is how we try to tell modern users about TLS. It's not perfect, though. It's just kind of an attempt to help users out. There are attacks on TLS. So here's kind of a classic one. If you remember your PRNGs, when PRNGs are not secure, bad things happen, and TLS was not immune to this. So I won't walk you through the specifics because it's kind of crypto heavy and we're trying to have fun here and just enjoy our blue slides. So basically, if you use a bad PRNG and the bad PRNG generates insecure random values, guess what? If you're using a bad PRNG, you can learn the Diffie-Hellman secrets, and now you're sabotaging TLS with Diffie-Hellman. So you have to make sure your random values are generated securely, because if they're not, an attacker could try to learn your random values and then screw you over. So yeah, this is a little bit technical, but not that technical. So feel free to come back and read it. But in the interest of time and enjoying these slides, let's just skip over that. And let's talk about one big TLS issue. So there are lots of different kind of small intricacies to how TLS works. And it looks like we chosen to focus on this one. And this one is certificate authorities. So what does real world certificate authorities look like? Let's quickly recall what a certificate is. So if you don't remember from a couple minutes ago, the way TLS uses certificates is the server sends a certificate, so that has its public key, and it's signed by a certificate authority. The browser has to verify this. So to do this, the browser will check that the URL domain name matches the domain name in the certificate. So if I'm visiting google.com, I would like a certificate for the google.com server. So the browser will check this, right? If the server sends a certificate for evil.com when I'm trying to visit google.com, that something is an indicator that something is wrong. So I don't want that. Now, the browser is going to verify the signature in the certificate because it's signed by an authority. And usually the public key is hardwired into the browser. So the browser has a secure list of public keys that it receives when you download the browser. So as you download Firefox or Chrome or whatever, you're also downloading a list of public keys. And that's your trust anchor. You trust the keys that are built into Firefox or Chrome. And now we can use the built-in public key to verify the signature. Because I trust the built-in public keys, I also trust the certificate once it's verified. So that's how it works in TLS as a quick refresher. Okay, but there are a couple problems here, right? Like what happens if a server sends a certificate says, my certificate is signed by this certificate authority, and I look in my list of trusted certificate authorities and the public keys. What if I don't find it? What if I just get a certificate that's signed by some random person that I've never met before? That's a problem. And what does Firefox do? They usually give you this warning message. So when most people look at this, like if you're a regular human and you look at this, this is gibberish to you. If it's me, I just look at this, I'm like, huh? What? Go back, advance, what? And I just try to get around this however I can because I don't give a crap. I just want to visit my website. But since we're in a security class, let's slow down and actually read this stuff. So now we're really having fun. We're reading fine print. Isn't that exciting? So let's read this. This IP uses an invalid security certificate. Why? Because the certificate is not trusted. Why? Because the issuer certificate is unknown. I don't know the authority. Right? This server might not be sending the appropriate intermediate certificates. So maybe there's a chain back to the root, but it hasn't sent the full chain. Maybe I have to import an additional root certificate, right? So that's basically what this error message is trying to say. Now, of course, most people don't read this, but at least Firefox tried to tell you, right? So at least you were informed, even if no one has ever read this stuff until us. So congratulations, we're the first people in history to ever read this error message. Okay, so what does happen if this case arises? Like, what does the browser do? There are a couple of options. The first thing is to warn the user like we saw from before. So give the user a warning that something is insecure. Even if they can't read this gibberish, at least the user sees this. What is this? This is a gigantic insecure icon. Anyone sees this picture and knows, uh-oh, something is not secure here. They also see this message, your connection is not secure. That's pretty plain English to me. So at least we're telling the users that something is wrong. So what if the user decides, I don't care, show me the website anyway? Well, the TLS connection can still proceed. Nothing is stopping the TLS connection at this point. The only problem is we no longer have the guarantee that the user is talking to the real server. Because I cannot verify the certificate, I have no idea if this is the true public key or an impersonator's public key. So I still have kind of sort of encrypted communication. I just have no idea who I'm encrypting to. Is it the real server? Is it a fake server? I don't know. So I lose one property of TLS. What happens if we're talking to an impersonator? TLS is no good anymore, right? An attacker can read the messages, they can modify the messages because you are talking to an attacker impersonating the server. So it's a little bit risky, but it can be connected. You can connect, but it's not perfect. So this is a problem. And usually our solution is to warn the user. Okay, that's a problem. Let's say, so here's kind of a side topic, right? So let's say you want to verify a certificate authority yourself. Right? I don't know why you would ever do this, but let's say you're super bored and you want to play around with your browser and you want to verify your own certificates. So let's try to manually verify your own certificates. So I did this today, a couple hours ago with our CS161 website because I was preparing for this lecture, not because I was very bored, but let's actually do it. So you can try this at home. Feel free when you're done with this lecture and you're looking for more excitement, go grab a couple beers or something and verify some certificates for yourself. So what do? You go to the URL bar, click on the lock. If you click on the lock, it says connection secure. So it gives you that indicator that you're using TLS. But that's not enough for me. I want more excitement. So let's be more exciting. Let's click this arrow. Holy crap, I just clicked on an arrow and I got more information. What did I get? I got this verification thing that says verified by Let's Encrypt. Let's Encrypt is a certificate authority, as we'll see soon. So now we know which certificate authority has endorsed CS161.org. Whoa, okay, now we're in real high excitement territory, but that's not enough for me. I want to find out even more. So let's click more information. Holy crap, now we're really in the matrix or whatever. So I get this entire pop-up. Oh my God, this is so interesting. There's so much gibberish here for me to enjoy. This is an entire pop-up box that says page info for this page. On the security tab, I find out that there's a website. Apparently we don't supply ownership information. Okay. I find out who verified it. So I find out Let's Encrypt. Oh my God, I even know what time the certificate expires. Holy crap, that's incredible. Our certificate expires September 14th. And I find out some other stuff, right? I find out, oh my God, I know what I'm using to encrypt. I'm using TLS. I'm using AES 128 for encryption. I'm using GCM, which is the authenticated encryption mode. I'm using SHA-256 for something, I don't know, for hashes, I guess. I'm using 128-bit keys, and I'm using TLS 1.3. Hey, that's all stuff I recognize. So extremely boring, yes, but kind of cool, kind of. And it tells us if you don't know about encryption, it gives us a reminder of what encryption is. We're encrypting pages, and it makes it difficult for unauthorized people to view information. So it's unlikely that anyone read this page as it traveled across the network. So that's cool. Okay. I know everyone is already like pumped up, but I have one more excitement, which is this button is extremely tempting. I can not only look at the certificate, I can view the certificate. Holy crap, let's do that. And this is what you see. So in Firefox, it actually opened a new tab, which I didn't know it did. But here's the actual CS161 certificate for your enjoyment. There are a lot of tabs. Apparently, there's a crap ton of information. I'm showing you like a small fraction of it. So go home and read it all to your heart's content. But you can see some common stuff here, right? Like it was issued in the United States. It came from the Let's Encrypt Certificate Authority. The valid date, it started in June and it's going to end in September. So I guess all summer. And there's some other random key stuff down here. So yeah, if you want to try this at home, feel free to go home. I promise you it's safe. There's no risk to yourself or your friends, but you can now go home and view as many certificates as you want for any website that you want. And you can find out information like, what TLS am I using? When does the certificate expire? Who issued it? So exciting, okay. Let's get a bit more boring and talk about verification. So what happens if an attacker steals a server's private key? Well, if I steal a server's private key, the certificate should no longer be valid because this private key is busted. Anybody can impersonate the server if they have the private key. So I need to find a way to get rid of the certificate. And we talked about this also in the certificates lecture, which is why it's blue here because it's kind of review. But we talked about how it works. So you can use an expiration date. So if someone has stolen my TLS certificate for 161.org, right, it could be a problem. Now anyone can impersonate our website, but it's not going to be the worst because after September 14th, that private key will be useless because the certificate is no longer valid. So at least it's not the worst. Okay. So they do have an expiration date. Sometimes the expiration date is very far in the future, so the attacker could mess with you for months or even years. There's another solution, which is verification lists. So every so often, the certificate authority sends a list out and says, hey, everyone, these certificates are busted. Do not use them. And the browser will say, okay, I got you. Let's delete these. So that's another way to do them. And it depends on how often you download the list. So kind of a problem there. There's another version these days, which is this random protocol, which says, before you use a certificate, once in a while or always, if you want to be paranoid, ask the certificate authority again before you use it, is this valid? So ask it just before you use it. And the certificate authority, because they know all the certificates, why they say, yeah, it's still good, you're good to go. Or no, this is revoked, stop using it. And they'll sign this message with their key so we know it's from them. And that gives us a way to kind of check live that the certificates are still valid. So if you want to be super paranoid, you can turn this thing on. I actually don't know how, but presumably you can turn this thing on. And before every single certificate, you will always check that the certificates are valid and no one has stolen a private key. Okay, let's talk about trust anchors. Oh my God, I'm running out of time, but we'll survive. So I think we're almost done. How many certificate authorities are there? That's a good question. If you go to your browser and look at the list of certificates, there's actually a couple hundred, so 100, 200. But some of these are malicious, right? So it's not guaranteed. How do we trust these people, right? They're the trust anchors, so we have to find a way to trust them. And it turns out there are ways they can issue malicious certificates. A malicious certificate could say something funny like, this random person has Google's public key. Uh-oh, that's a problem, right? Or like, this attacker's public key belongs to Google. So now this attacker has the power to impersonate Google. That could be extremely dangerous. And it has happened before that some random person just suddenly obtained all of Google's power. There are some reasons. You could hack the certificate authority. You could even just bribe the certificate authority and say, I'll give you this pile of money if you give me a malicious certificate so I can impersonate Google. And some certificate authorities actually are corrupt enough to just take the money and run. So that happens sometimes where someone just suddenly gets a Google certificate and is allowed to impersonate Google because some certificate authority accepted a giant pile of money. So those are real world trust anchor issues that you have to deal with when you're running TLS. Here are some examples. Here's a solo hacker who stole a certificate. Here's another article about that. Sorry, we'll go fast. This one shows that the entire server was compromised. This one shows that they had been compromised years ago. Oh God, that was terrible. So this was DigiNotar, which was one of the certificate authorities. It used to be in all the browsers. Then it got hacked. And what did the browsers all agree on? The browsers said, you got hacked, screw you. And what they did was they nuked DigiNotar out of its list of trusted CAs. So they were like, we trusted you, but you betrayed our trust by getting hacked. So no more for you. And this company basically just went down, I think. So if you're not careful and you let your certificate authority company get hacked, it's bye-bye for you. Every browser in the world just deleted this company from existence. So that's kind of rude, but deserved, right? Like they got hacked, so they had it coming. This one was like WoSide. This one was just not trustworthy at all. I guess they were also having like shady deals where they were selling off certificates to attackers, and people found out about this, and every browser just said, you know what, screw you too. And so WoSide got deleted from all browsers as well. So takeaway from all this stuff is it's very hard to trust root anchors in TLS. Although in certificates, we talk about how we implicitly trust someone, in reality, we actually have to find a way to trust them. And that can be hard because human trust is hard, right? We can trust someone and have our trust betrayed, as these two certificate authorities showed us. Okay, and how do we solve it? There are a couple solutions here, but in the interest of time, we'll skip over them, but feel free to read them later. Yes, and then let's quickly talk about a certificate authority example. I think this is the very last slide, sorry, but this is kind of interesting because we talked about it before. It's called Let's Encrypt. So TLS requires everyone to maintain certificates, right? This used to be hard because some companies say, you want a certificate? I'm going to ask you to pay because I have to keep my company running. So TLS used to actually cost money. So if you wanted an HTTPS website, you had to pay up. There was some management overhead because you had to have someone smart on your team to generate certificates. It was not easy to do that. So this was a problem. So some organization came together and said, let's encrypt. And they made that their company title. And they said, let's make encryption super easy for everybody. I don't want certificate authorities to be this complicated thing that you have to pay money to access. I want the world to be HTTPS encrypted. What a noble mission. And they made it so easy that they are actually now the world's largest certificate authority. So CS161 uses Let's Encrypt. Do you know why we use Let's Encrypt? Because it's free. It does not cost money. So our certificate for CS161 cost us $0, and it will always cost us $0. And it's extremely easy to obtain certificates. None of us on staff are like sysadmins or anything. I literally just checked I checked the HTTPS button on GitHub. So we use GitHub Pages, and I just checked enable HTTPS, and boom, Let's Encrypt automatically sent us a certificate for free. So these people are awesome. I think there's like a bunch of nonprofits doing this, but they have become the world's largest certificate authority because they are free, and their goal is just to make it easy for everybody in the world to use HTTPS. So thank you, Let's Encrypt. Sometimes in security, there are some real heroes, and these people are real heroes. And here's the process for doing it. It's so easy that I can just check a box or automate it with a script. Life is good. Okay, we've reached the end, so let's go back and talk about a summary really quickly. If you have to go, sorry, we're running late today. But here's the handshake, as we talked about before. It has nonces to make sure every handshake is different. This prevents free play attacks across connections. We have a way to prove the server's public key with a certificate. We use either RSA or Diffie-Hellman to prove that the server owns the private key and to help them agree on a shared secret key. We use MAX to make sure nobody's tampered with the handshake. And then eventually we can send messages with symmetric encryption and MAX. And to prevent replay attacks within a connection, we add record numbers inside the encrypted messages. Then we talked about security properties. Diffie-Hellman has forward secrecy, but RSA does not. There is end-to-end security, so everybody can be malicious, but TLS is still great as long as you're talking to not an attacker. It's not anonymous. There's no availability. Attackers can figure out who you're talking to, and they can drop your connections. The application layer can use TLS for secure communication, so HTTPS lets you visit websites securely. And finally, we had a long talk about certificate authorities and how sometimes trusting them can be hard because human trust is hard. That is finally the end. Does anyone have last questions? Sorry, the entire back half was super fast, but it was mostly optional, so I think we're okay. Okay, if there are no other questions, I hope tomorrow is shorter, but some of these lectures are a little bit dense, so fingers crossed, but we'll see you tomorrow.